morning, everybody. All right, today we're going to do one section. We're going to do prime and composite numbers because it's the last day of the week and spring break is next week, so everyone should start early. The relationship between a composite number is made up of prime numbers. All right, so that's the relationship between composite and prime numbers. So the question is now, what does all this stuff mean? So prime numbers are only divisible by 1 and itself. In other words, the remainder is 0, so there's no remainder. When we introduce these to kids, graphically or using blocks, prime numbers cannot be represented by squares or rectangles, rectangles. Using blocks. Prime numbers cannot be represented by a square or a rectangle having more than one row. And that in itself is pretty interesting. Because again, depending on how well the kids know division, they can't really use the first test. A prime number is only divisible by itself or 1. So we use blocks. So give me an example of a prime number. Right. Because I cannot use, if I use blocks, I cannot make it a perfect square or perfect rectangle using blocks. Are prime numbers ever odd numbers? Exactly. Good catch. Yes. Prime numbers are never even numbers. Why? Right. If it's an even, if the last digit is an even number, that means the number's even, it's divisible by 2. So prime numbers always odd. numbers. Are all odd numbers prime? Give me an example. Exactly. 9 is made up of 1 times 9, or it's made up of 3 times 3. Again, if you use blocks, you can make a perfect square out of this one, or a perfect rectangle with more than one row. Do you remember the formula for odd and even numbers? Two times any number is the definition of an even number. Because, again, if it's divisible by 2, that means it has to be multiplied by 2. An odd number is 2n plus 1. And this plus 1 is what makes the prime number a prime for those that are primes. So prime numbers, examples of them: 1, 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, and so on and so forth. So on your little sheet here, you get your example sheet, because we're going to look at that table there. What do you think, by looking at this table, what do you think it means? What do you notice about this? Look at the second column. In the first and second column, do these numbers look familiar? If yes, what do they look like? They're all prime numbers. 1 is the only number that's divisible by 1, only has one divisor. These other numbers have 2 divisors. What does that mean? What number is a divisor? Mathematics is, I try to stress, first day of classes, mathematics is a language. It all bases itself on definitions. You have to know what these words mean to be able to answer it. So what part of a fraction is a divisor? No, that's a dividend. That would be the bottom number. So for example, 2 is divisible by what? 1 and 2. 3 is only divisible by 1 and 3. 17, only divisible by 1 and 3, or 1 itself. How about 4? What does this 3 mean here? Yeah, the number 4 is divisible by 1, 2, and 4. There's 3 divisors. The number 9, 1, 3, 9. The number 25, 1, 5, 25. Only has 3 divisors. Look at the number 16. It's under the column of 5. 16, it says that there are 5 divisors that divide 16 with 0 remainder. What are they? What numbers make up 16? 1 times 16. I always start with the obvious one first. Increase this one, decrease this one. So 2 times what? And then 3 times, no. Does 4? 5, 6, 7, 8. So we only have 1, 2, 3, 4, 5. These are the 5 numbers. So that's what that table is used for. It tells you how many divisors it has. All right, let's look at example 9 on the next page. Example 9. Show the following are composites or composite numbers. A, 1, 5, 6, 4. How do we know that's a composite number? Put your phone away. You don't need it. What's a composite number? What's a composite number? What's a prime number? Right. If it's not a prime number, it's composite numbers made up of prime numbers, more than itself in 1. So how do we know this is a composite number? It has a 4 right there, which we know that means it's divisible by 2. Just that alone tells us it's a composite. As soon as you find one number that's not itself or 1, that means it's a composite. Because it's divisible by 2. B, 2, 7, 8, 1. In order to be divisible by 2, the last digit has to be even or 0. Oh, well, look at the sheet I gave you yesterday, all the divisibility rules. For all the divisibility rules. So we know it's divisible by 2 if the last digit's a 0 or an even number. What's the rule for divisible by 3? Mm-hmm. Is this one? In other words, if I take 2 plus 7 plus 8 plus 1, 7 plus 2 is 9, 8 plus 1 is 9, is 18. Is 18 divisible by 3? Yeah, it equals 6. So this number is divisible by 3. C, 1001. 1001. Okay, for quickness, we know it's not divisible by even numbers. So 2, 4, 6, 8, 10. We know it's not in any of those. We know it's not 3. How about 7? 7 is not it. It's some of the digits. How about 11? Let's look at 11. It says a number is divisible by 11 if the sum of the digits in the even spaces minus the sum of the digits in the odd spaces is divisible by 11. The even spaces, the first, these are the first and the third, second and the fourth. So it says the sum of the even spaces, 0 plus 1, minus the numbers in the odd spaces, 1 plus 0. What does that equal? Yeah, this 0 plus 1 is 1. Is 0 divisible by 11? Yes, it is. It's 0. It's a whole number. So it's divisible by 11. I know. You'd think not because it comes out to be 0, but a number can divide by a number. A 0 can be divided by a number, not the other way around. So this is totally legitimate. It just looks weird. All right. So what's D? D is 3 times 5 times 7 times 11 times 13 plus 1. This one, again, the stronger you know your rules of math. So let's look at this. If I take numbers 1 times 3, it's going to equal 3. Odd number. 3 times 5 is 15. Also odd number. If I multiply two odd numbers, I get an odd answer. There's no way it can equal even. So if I multiply all odd numbers, what is this going to give us? It's going to give us an odd number. just for this. If you multiply odd numbers, you get an odd answer. And if you have an odd answer and you add 1 to it, what does it become? It becomes even. And even numbers are divisible by, so it's a composite. Pretty tough questions. Just think, they want kids in elementary school to know this stuff. So yeah, but this one goes by the rule that the product of two or more odd numbers will be odd. Again, did you all know that? Not really. I said these are the basic structures of math that we have to learn. And fortunately, when you're teaching this to your kids, all this stuff comes in the learning process of the kids. When you first teach them multiplication, you start saying, hey, let's see what happens. If we take an even number times an even number, what's that going to equal? Even. If we take an odd number times an odd number, it's going to be odd. How about an even number times an odd number? Well, let's see. 2 times 7. Odd or even? 9 times 4. 36. 10 times 9. All these numbers are what? Even. So there's something you knew at one point in your life, but forgot. See, you learned something new this semester. My job is done. Next part. Prime factorization. What does that mean? What does factorization mean? What's that? Give me an example. The numbers, yeah, okay, yes, that's true. So if I take 3 times 4, that equals 12. Yes. And those are the factors parts. Yes. Which is, but what you said is actually a great example. If you, what two numbers you multiply together equals a product, these are the factors of that. In other words, factors are what's made up of it. The first introduction you get of factorization is in this rule. What do you do if you have that? So this is called the distributive property. So this becomes a times x plus a times y. Yeah, going this way is distributivity. Going this way is factoring. Factoring is when you take a common equation and make it two separate products. So what do they have in common? They both have an A. We take that out. So that's its own parenthesis. Like you said, you have the parentheses. And yes, you saw this in algebra. What are the factors of this polynomial? What makes up x squared? X times x goes in the first spot because that's in the first spot. What do you do next? Now you look at the signs. Look at the second sign. This one's important because this number comes from this times this. And the only way it can be positive is if the signs are the same. So you look at the first sign. Since the first sign is a plus, that means both of these have to be the same. They have to be plus. If it was a minus, they'd be both be minuses. Now comes the hard part. Take the number, the first number here, times this last number. So 1 times 6. Then you got to figure out what two numbers multiply to give you 6, that when you use that sign, when you add them, you equal this number. What times what is 6 when you add them, you get 5? 3 times 2, or 3 and 3 plus, or 2 plus 3, 2 times 3, yeah. And since they're both the same signs, it doesn't matter which one goes where. I know this is not part of this section here, but you want to do some more of these type? Okay, this I'll show you. That's what if we had this? Factor that one out with the same logic we just had. So what goes in the first spaces? X and X. What about the signs? Remember, if the second sign's a plus, that means they're the same signs. It's whatever the first. If the second sign's a minus, then they're opposite signs. And the bigger number gets that one. So now we look at 1 times 15 equals 15. So what times what equals 15? That when we subtract them, we get 2. Yeah, 5 and 3. 5 minus 3. And the bigger number gets the plus. So the 5 goes here and the 3 goes there. Okay, ready for another one? Let me do this one. Okay, so I want 6x squared minus x minus 15. This one's going to change a little bit because what goes in the first spot? It's no longer x and x. This is where it gets complicated. Because up until now, our leading coefficient has always been 1, and we can do that. So if it's not a 1, then it's made up of 6x and 6x. We'll fix that later on. The second sign's a minus. What does that mean? If the second sign's a minus, that means there have to be opposite signs. Because a positive times a negative gives me a negative. And the bigger number gets the minus sign. So we do the same thing. We take the first number times the last number, 6 times 15, we get 90. So we got to figure out what times what equals 90. That when we subtract them, we get 1. Yep. 10 times 9 is 90. 10 minus 9 is 1. So since 10's a bigger number, it gets the negative sign. So 10 goes here, the 9 goes there. We're not done yet. This is the first step. Now, look at both of these equations here. Do they have anything in common? Do these have anything in common? Is what? So 6 and 9, do they have any number in common? 3. They both have a 3 in common. So to figure out what goes inside here, divide both of these by 3. 6 divided by 3 is 2. 9 divided by 3 is 3. The same thing here. What do they have in common? Yeah, they both have a 2 in common. So divide both of these by 2. 6 divided by 2 is 3x. 10 divided by 2 is 5. Whatever you factored out, erase, delete it. And that's your answer. That's factoring in a nutshell. Well, not prime factorizing, but that's factoring, which you guys, one of the hardest parts in algebra people have trouble with. But that's how easy it is. You learn one rule, you can do them all. If they're divisible, if they're factors of each other. If not, then we have to use other rules. But let's get back to prime factorization. What prime factorization means is, let's say I had the number 18. I want to know what numbers make up 18. The easiest way to do this is by the tree diagram. Start with the easiest. What's the easiest numbers? What makes up 18? What times what? Yeah, then we're back to 18. Okay, the second easiest. Yeah, 2 times 9. Can you go any further with 2? No. So that's a prime number. How about 9? Can we go any further there? It's made up of 3 times 3. And 3s are prime numbers. So there's the prime factorization of 18. So prime factorization means reducing a composite number down to its prime numbers. That's prime factorization. Reducing a composite number into its basic prime numbers. And this is why that sheet I gave you is important. That sheet goes all the way to 13. Why does it stop at 13? Because if it's 14, if you go to 14, well, that's the same as 2 and 7. 15 is the same as 5 and 3. So what if I gave you a bigger number? Prime factorized 260. If a number ends in 0, what do we know about it? Yeah, that means it's divisible by 10. 26 times 10. If it ended in 2 zeros, then it's divisible by 100. It would be 26 times 100. So the number of zeros tells you what it's multiplied by. So now we go from here. We got easier ones. 26 is made up of what? It ends in a 6, so we know it's divisible by what? It's divisible by 2. 2 goes into 2 once. 2 goes into 6 3 times. 2 is a prime. 13 is a prime number. 10 ends in a 0, so it's divisible by 2. 2 goes into 10 5 times. So the prime factorization is 2 times 2 times 5 times 13. And what another way you can write this, since you have 2 2's here, you can write 2 squared. Because 2 times 2 is just 2 squared. One more. 128. Because it ends in an even number, we know it's divisible by 2. 2 goes into 12 6 times. 2 goes into 8 4 times. Again, 64 ends in even, so it's divisible by 2. 2 goes into 6 3 times. 2 goes into 4 twice. Ends an even number. 2 goes into 3 once with 1 left over. And 2 goes into 12 6 times. 2 goes into 16 8 times. 2 times 4. 2 times 2. 3, 4, 5, 6, 7. So the answer is 2 to the 7th. Again, you have to practice this. You have to know how to do this because you have to try to explain it to kids. Third, fourth grade, I believe. Because in kindergarten, first grade, they're learning the basic rules of multiplication. And then about third grade, they should be able to factor. Because it's just the opposite. It's really just division. How many ways can I divide this thing? And that's where you introduce. So third or fourth grade, I would say, when they start being tested. This leads us to theorem 4-12. The fundamental theorem of arithmetic. It's on your sheet. It says every composite number can be written as a product. What does product mean? Multiplication problem. Yeah, so can be written as a multiplication equation of prime numbers in one and only one way. Except for the order of those numbers. What does that mean? So a composite number, say 18. We know, and we just figured out, it's made up of 2 times 3 times 3. Those are the only numbers, prime numbers, that make up 18. Well, times 1 also. One's in everything. That's what we call unifier. So, or I can write 3 times 2 times 3 times 1. So the order is not important. It's just that these numbers, there's only one set of numbers that fits. That's what the fundamental theorem of arithmetic tells us. All right, let's take the next section, next part. The number of whole number divisors. So what does that mean? What do you think this topic is about? Number of whole number divisors.
How many times could 18 be divided?
Not the number of times, it's what numbers divide 18. So the number of, in other words, how many, if my divisor is 18, how many whole numbers, prime numbers, are made up of there?
So it could be units to or just
Everything, yeah. Because, for example, if it was 18 divided by 9, 9 is made up of 3 times 3 or 1 times 9. So all those. So the theorem 4-13 states if D is a divisor of some number n, where n is not equal to 0. Why is that an important concept? If D is a divisor of some number n, where n is not equal to 0, why is that important? If 0 is on top, what's the answer going to be no matter what? It's always going to be 0. So it doesn't matter what the divisors are. So we're saying that n is anything other than 0. It's a whole number, anything other than 0. Then what was I? Then the equation n over d is also a divisor of n. What does that mean? If d is a divisor of some number n, where n does not equal 0, then n over d is also a divisor of n. So let's look at this. D is a divisor of n. Give me an example of what that means. D is a divisor of N. Maybe 4/2. But that's a bad one because 4 is made up of repetitives. Let's look at 18 divided by 9. This is N and this is D. So we know that D9 is a divisor of 18. Why? What is 18 divided by 9? 2. So since we know 9 is a divisor, then this answer here is also a divisor of N. Or 15 divided by 3 equals 5. That means 15 can also be divided by 5, which gives us 3. That's what that's what the whole number divisor tells us. Which brings us to another theorem. There's theorems for everything. The next theorem is 4-14. If P and Q are different prime numbers and N and M are whole numbers, then what has to be true? Then P to the power N and Q to the power M has N plus 1 times M plus 1 whole number divisors. What does that mean? P and Q are different prime numbers, and N and M are whole numbers. Then P to the power N times Q to the power M has N plus 1 times N plus 1 whole number divisors. Think of what this means. If P and Q are prime numbers. Give me an example. Give me 2 prime numbers. 5 and 11. And give me M and N. Let's say 2 and 3. Actually, no. For simplicity purposes, let's use 3 and 5. Because what we have to do here is 11 times 11 times 11. Yeah. So let's use 3 and 2 here. So that's our P to the power N. This is our Q to the power M. Remember, they're multiplied. So what does this really tell us? This thing means 3 times 3 times 3 times 5 times 5. All of these numbers are divisors of the final answer. We have 25 times 9, 25 times 27. 675. So multiply all these together, we get 675. So All of these numbers are divisors of 675. But so is 3 times 3. So is 3 times 3 times 3. So is 3 times 5 or 5. Each one of the combinations of these numbers are also divisors. Since these are all prime factors, I can combine them any way I want to, and they're divisors of this number. So what that tells us is we have 3 plus 1, 2 plus 1. There are 12 divisors that we get, 12 different combinations we can make of these numbers. This is one of them, all three of them, or all five of them, I mean. We could just use 4 of them. We could use 3 of them. We could use 2 of them. We could use just one of them. Or we could make combinations thereof. There are 12 ways we can combine them. That's what it tells us. Example 10. Find the number of whole number divisors for the following. A, we have 1 million, and we have 210 to the 10th. How would we go about doing this? So how would we rewrite that one? What's the easiest way of writing 1 million as an exponent? Since there are 6 zeros, what that means is that's 10 to the 6th power. The number of zeros is your exponent times 10. What is 10 made up of? 2 times 5, or 5 and 2. So what this means is I could distribute those. 2 to the 6th, 5 to the 6th. So how many whole number divisors do we have? What do we have to do to the exponents? Remember, this is n, and that's m. 6 plus 1. 6 plus 1. We have 49 whole number divisors. That's what it tells us. Let's do something similar with this one. So actually, we can rewrite this equation here, the power 10, as 21 times 10. And that power 10 stays there. What is 21 made up of? 3 times 7. And 10 is made up of? So these are all multiplied. So what I have 2 to the 10th times 3 to the 10th times 5 to the 10th times 7 to the 10th. Everybody follow that so far? These are, I made the inside prime numbers and I raised them all to the 10th power. So how many prime whole number divisors do I have? Well, you have to take each one of these and add 1 to them. That's what the theorem just told us. So we have 11 times 11 times 11 times 11, which is 11 to the 4th. Whatever that is, that's what your answer is. Make sense? So it's going to be well over 10,000, but it's less than 20,000. It'd be between there somewhere. Okay. The next section. Determining whether a number is prime. That sounds pretty straightforward. We have an example. Yeah, with 2 theorems here. How would you think about go about doing this? How would you determine if a whole number is prime? I'd go by all the rules of divisibility to see does the last digit end in a 0 or an even number? Is the sum of all those numbers? So go through all those rules, and that's how you determine. So let's look at the next 2 theorems. Theorem 4-15. It says this. If n is composite, it is a composite number, then the number n then the number n has a primary factor, we'll call this p, such that the primary factor p such that the p squared is greater than or equal to n. Well, let me see. It can't be.
So,
It's going to be less than. Yeah, because it can't be. Yeah, but it has to be smaller because it's made up of those terms. For example, is n is 4. 4 is a composite number, correct? It's made up of 1 times 4, 2 times 2. A primary factor is 2. If I square 2, is it less than or equal to 4? Yes, it's equal to 4. Theorem 4-16, this one says that if a composite number n is greater than 1. And n is divisible. What's, oh no. Okay. Prime, actually, it's be more, but by a prime number p such that p squared is less than n, then n is a what? So if a composite number n is greater than 1 and n is divisible by a prime number p such that p squared is less than equal, then n has to be a prime number. Let's look at the examples here. Example 11 is,
Where it says if A is a composite number, wouldn't it be a whole number, not a composite number?
oh yeah. Yeah, it's a whole number. Okay. Because we have to, the reason that's important is because we have to limit ourselves to the whole number domain, where it's from 0 to infinity. Because the next thing we're going to do in the next chapter is we're going to now increase it to all integers. Now, is 397 composite or prime? So you have to go through all those rules of divisibility. We know it's not divisible by 2 because it doesn't end in even or 0. Is it divisible by 3? In other words, if we add these numbers, 3 plus 7 is 16, plus 3 is 19. Is 19? No. It's not divisible by 4, not divisible by 5, because it doesn't end in 0 or 5. Not divisible by 6, because it's not divisible by 2 and 3. 7 is a whole different rule, but it's not divisible by 7. Neither with 8 or 10. So what do y'all think? Is it a prime number or not? Because what number do we stop at? Because we know that it's not divisible by 2, 3, 4, 5, 6, 7. Or 6, 7, 8, 9, 10, 11. When do we stop? At what point do we know it's going to be a prime number or not? We have to go with this. These are our P's. We keep on going until we get to a P value, and when we square it, it's greater than N. Okay, now from here, from 11, we don't have to do 12. We're just looking for the prime numbers now. Is 13, 15, not 15, 17, 19, 23. Well, 23 is too far. Because if I square 23, I get 529. Too big for that one. So I can't go to 23. How about 19? What's 19 squared? 19 times 19, 81, 361. So does 19 fit in there? Are you sure? So what would multiply by 19 to equal? I mean, yes, it satisfies this condition, but is 19 a divisor of 397? No. So we have to stop at that number. If we go to 20, that's too much. So the highest number we can go to is 19. We have to check all those numbers, see if they're divisible into there. Only the prime numbers. Because divisible, P has to be a prime number. So we only have to look at 1, 2, 3, 5, 7, 11, 13, 17, 19. Those are all the numbers we have to check. Anything over 19 won't satisfy this condition. So because of that, we know that 397 is a prime number. Because none of these are divisible into there. I really hope they would have done it backwards. I wish they would have given you like B says, is 91 a composite or prime? It would have been easier starting off with a smaller number than something like this one. So is 91 a composite or a prime? Remember, we have to find a prime number squared that's less than or equal to 91. So it's 1, 2, 3. What's the next one after 7? That's a prime number. 8's not, 9's not, 10, 11. Is 11 times 11 is bigger than 91. So we have to only check these numbers. Is 2 divisible in there? No, because it doesn't end in an even number or 0. Is 3? No. 9 plus 1 is 10. That's not divisible by 3. Is 5? No, because it doesn't end in a 5 or a 0. How about 7? Where's my sheet? Let's look at, figure out 7. A number is divisible by 7 if the last digit is multiplied by 2 and subtracted from the remaining numbers. So 1 times 2 is 2. Take this number, subtract it from the remaining numbers. So 9 minus 2 is 7. Is this number divisible by 7? Yes. So 91 is divisible by 7. So does that mean it's a prime or a composite? It's a composite. What are perfect squares? In elementary school, we could also teach this, because what is a perfect square? What is a square? You have the same number of rows and columns. So 4 is a perfect square because it's made up of 2 times 2, which is 2 squared. 9 is made up of 3 times 3, which is made up of 3 squared. And so on and so forth from there on out. You have 16 is made up of 4 times 4, which is 4 squared. 25 is 5 times 5, 36, 49, and so on and so forth. Because you can now represent those as perfect squares. All other composite numbers are all other composite numbers are made up of rectangles. So that's what a perfect square is. Infinitude of prime. So to define this, perfect squares are numbers that you can make them into perfect squares. It has the same, the product is made up of the same numbers horizontally and vertically in the rows of block. What is that? Infinitude. Does the list of prime numbers ever end? Not that we know of. I mean, we just found out that 379, what that was a prime number. That's a pretty big one. So we find out what the next one is and what the next one is. And that's baffled mathematicians for a long time. Is there really an end? So they have computers running it, and they see how far they can get to the perfect prime numbers, and it's still going. So, to what we know so far, no, there is no end. Which is amazing, because if you think about it, all these conditions have to apply for, let's say, a 12-digit number. And the chances are, again, is the last digit even? So we know all those are gone. Zeros, no. Fives, no. Or if we add the last 2 numbers or the last 4 numbers. So it's what we know so far, no, doesn't end. But for our lifetime, we just need to know the basic ones. We have another example here. This is problem solving. How many bears? A large toy store carries one kind of stuffed bear. On Monday, the store sold a certain number of bears for $1,843. On Tuesday, without changing the price, the store sold a certain number of bears for $1,957. How many toy bears were sold in those 2 days if the price of each bear was greater than $1? Number of bears sold. So day 1, they sold 1,843. Day 2, they sold 1,957. So how would you go about doing that? How does this relate to what we're doing with? And it's also an excellent way to segment into next section is least common multiples, greatest common divisors. What we have to do is take both of these numbers separately and find the largest number that they both have in common. Same multiple in both of these. And when we do that, we're going to see that they both have a multiple of 19 because we're running out of time. So 19 times what is that? How do we figure that? If I want to know 19 times what is equal to this, how would you find that? Yeah. 1843 divided by 19 is equal to 97. And then same thing is 1957 divided by 19 is 103. Since the cost remained the same in both days, this was the cost of each bear. This was the number of bears sold. So we sold approximately 200 bears. That's how you use this stuff. Find the common multiple, and that multiple is the price. All right, I'm letting you off just 1 minute late. Go enjoy the spring break. And today is supposed to be rainy this evening and a cold front coming through. So be careful.
Supposed to be spring or?
I'm not buying into that. I'm still